Hello everyone, my name is Subramanian and welcome to my video lecture on inter-process communication. Here, we'll be discussing inter-process communication concepts briefly. Let's get started. So here we have the topics we're going to be talking about over the course of this video. We'll start with what a process is, what are the types of processes, and how can we create a process. Then we'll move on to inter-process communication. We'll find out what inter-process communication is and exactly why we need it, after which we'll talk about synchronization, where we'll again talk about what it is, why we need it, but also how we can achieve it. Moving on, we'll be talking about inter-process communication methods, where we'll understand how inter-process communication is implemented, and finally, we'll conclude with a summary and closing notes. So let's begin. Introduction. You may have noticed that I've used a lot of terms: process, program, communication. Well, what are they? Basically, all devices have some sort of process management, whether it's your laptop, your computer, your phones, your TVs, all of these have processes. And the reason being that this ensures you can use your applications easily. You as the user don't have to worry about what's happening in the background. You have the luxury of simply using the application while the operating system takes care of the rest. Now, you may have also noticed that if you ever open the task manager, you'll notice a bunch of processes that are present here. And this is what we're going to be covering in this video lecture. How do these work? How do so many processes work with each other to give us what is an operating system? Before we can move on to how, we need to know what. So what exactly is a process? Well, a process is nothing but a program in execution. And now you have the question, what is a program? Well, in the simplest sense, a program is a file that contains the information about a process and how to build it during runtime. When you start the execution of a program, it's loaded into the RAM and starts executing. Each process has a unique process ID by which it is identified. The ID is useful in process creation, identification, and termination. Well, how do we create a process then? It's simple. We use the fork system call. Now this fork system call gives us two processes when we call it, the parent and the child. So if you see here, calling the fork produces two processes and every subsequent fork also produces two processes. But how do we know which is which? Well, fork system call returns a value, and if the returned value is 0, that means that we are in the child process. If the returned value is greater than 0, it indicates that we are in the parent process, and the value that has been returned is actually the ID of the child process. And finally, if the returned value is less than 0, that means that an error has occurred and therefore it was not able to create the processes. Now, in the same way that we use fork to create a process, we can also use the exit system call to terminate processes. But there's also a chance they may end abnormally. Independent versus cooperative processes. An independent process is just that. It's a process that executes independently. Now, this process is neither affected nor does it affect the execution of other processes. Simply put, this process executes by itself and does not care what all the other processes are doing. Whereas a cooperative process is a process that is affected by and can affect other processes. Now, you may think independent processes have to be more efficient, right? Because they're running by themselves, we can allocate the RAM to them, get it done faster, and so on. But the reality is that there are many situations in which the cooperative nature can be utilized, for example, for increasing computational speed, convenience, and even modularity. We'll go through exactly how later on. Now we get to the main topic, inter-process communication. So what is it? It's a mechanism provided by the operating system that allows processes to communicate with each other. Now, this communication could involve letting another process know that some event has occurred or the transferring of data from one process to another. So, both of these are examples of inter-process communication. Now, here's a question for you. What would you think is the most important thing that has to occur between processes during communication? The answer? Synchronization. Two processes have to be synchronized before they can communicate. Now, what is synchronization? It's nothing but the coordination of events to operate a system in unison. So, you need to synchronize processes before you can communicate between them. And how do we achieve that? We have four methods. We can use semaphores, mutual exclusion, barriers, and spin lock. Of course, the question in your mind now is why? I mean, yes, I told you that synchronization is very important, but why is it important? To understand that, let's take a look at critical section. Now, critical section is a code segment that accesses shared variables and it has to be executed as an atomic action. It means that in a group of cooperating processes, when you have multiple processes that are cooperating with each other, at a given point in time, only one process must execute its critical section. If any other process also wants to execute its critical section, it has to wait until the first one is finished. Now, if this isn't handled properly, it can lead to a race condition. So if you notice here, we have a process and it accesses a part of a code. So it accesses some shared variables. At the same time, if you have multiple processes accessing the same variable, the same shared space, that leads to the race condition. What's a race condition? A race condition is just a condition that occurs inside the critical section when two or more processes read and write the same variable. It's a concurrency problem essentially, where each process has its own sort of, it has its own version of the variable, and what this causes, consequence of this, and the consequence of this is that now you have the same variable which was accessed from the same shared memory space with two different values in two different processes. So there's a big possibility that the output of one of those output present in one of those processes is wrong. So this is due to several processes accessing and processing the manipulations on the same data in a concurrent manner. The outcome will obviously depend on the particular order in which the access of data takes place. So for example, if you have process 1 and process 2 accessing the same space, and process 1 modifies it first, then process 2's value will depend on process 1's modification. So to avoid critical section and race conditions, we need to achieve synchronization. How can we do that? There are four methods we discussed before. Let's go through each of them. First, we have semaphores. Semaphores are just variables that control the access to a common resource by multiple processes. The two main types are binary and counting semaphores. At its core, semaphores are just signaling mechanisms. A process that is waiting on a semaphore can be signaled by another process. It has two atomic operations which are wait and signal. They are machine independent and are implemented in the machine independent code of the microkernel. However, a disadvantage of semaphore is that the programming of it is actually quite complicated, so there are chances of not achieving the synchronization itself, and it's not practical for large-scale applications. Next, we have mutual exclusion, which requires that only one process can enter the critical section at a time. This is useful for synchronization and also prevents race conditions. Now, mutual exclusion comes into the picture when two processes work on the same data at the same time. It acts as a sort of a lock, and when a thread tries to acquire a mutual exclusion, it gains the mutual exclusion only if it's available. Otherwise, the process has to be set to sleep condition. It reduces the latency and busy waits using queuing and context switches. The third way we can achieve it is using a barrier. Now, a barrier does not allow individual processes to proceed until all the processes reach it. Many parallel languages and collective routines impose barriers. It's basically just a type of synchronization where all the processes have to wait until they've reached a particular point of execution. Now, synchronization barriers can be shared across different processes, making it even more useful. Finally, we have spin locks. This is also a type of lock. The process trying to acquire this lock will wait in a loop, constantly checking if the lock is available or not. So this is known as busy waiting because even though the process is not doing anything, it's still repeatedly checking to see if the lock has been opened. Once it has, it gains access to the critical section of the code. And the problem with Spinlock obviously is the high CPU utilization because of the constant looping and checking to see if the lock is open. Now, earlier we discussed certain small advantages of cooperative processes. So you're probably wondering, why do we need inter-process communication? Inter-process communication provides greater computational power. Now that we can have processes cooperate with each other, we can have them do more complex tasks. It aids OS with communication and synchronization. So across the entire operating system, the communication and synchronization is improved. We have greater modularity. We no longer need to program processes to work independently. We can program them to work with each other. And it increases the efficiency of the software. Obviously, having two processes cooperate will be faster than having processes independently accomplish their tasks. Moreover, it uses shared memory for communication and limits the remote procedural call communication on the local machine, thereby again increasing the efficiency of the software. Let's take a look at the inter-process communication methods. The main inter-process communication methods are pipes, sockets, files, signals, shared memory, and memory queue. Files. It's nothing but a data record that is stored on a disk or acquired on demand by a file server. So, multiple processes can access a file as required, and all operating systems use file for data storage. Now let's take an example. We have two processes, one is reading and the other is writing, trying to access the same file at the same time. What happens here? Well, based on priority, first in first out or predetermined order of arrival, the read and write actions are executed. So for example, process 1 arrived before process 2, therefore process 1 will read the file, complete reading the file, and then only process 2 will be allowed to write. Concurrent reading and writing will not occur. In the same way, if we assign a priority, say process 2 has greater priority than process 1, process 2 will be allowed to write, then finish, and then only will process 1 be allowed to read the file. Our next method is using sockets. So sockets provide point-to-point two-way communication between processes. They are simply endpoints for sending or receiving data in a network. This is true for data sent between processes on the same computer or data sent between different computers on the same network. There are a couple different types of sockets. First being sequential packet socket. It provides a reliable connection for datagrams whose maximum length is fixed, and it is two-way as well as sequenced. Then you have the datagram sockets, in which the receiver may receive the messages in a different order than which they were sent. You can sort of imagine a datagram socket similar to sending mail from one location to another location. Third, we've got a stream socket. They operate very similar to telephone conversations and provide two-way reliable flow of data with no record boundaries. The data flow is also sequenced and unduplicated. Finally, we have raw sockets, where we use the underlying communication protocols to access the sockets. The advantages of sockets include easy debugging, usable across multiple systems, and scalability, whereas the disadvantages include high overhead, security flaws which need to be addressed. Third, we've got pipes. Now, a pipe is a data channel that is unidirectional, but we can use two pipes to create a two-way data channel between processes. Now, we use the first in first out queue in order to standardize which process is supposed to be completed first. And we also use an array which stores two pointers. One pointer points to the input end and one pointer points to the output end. You can think of a pipe as a sort of like a bucket where one person pours water into the bucket and the other person takes water out of the bucket. Now, for every process, we have three descriptors: the input descriptor, the output descriptor, and the error descriptor. We'll go over these in detail in the next slide. The limitations of pipe include the fact that it's one way. I mean, you can't have a two-way pipe unless you use two pipes. It cannot broadcast, meaning that one input can't broadcast to multiple output processes. And lastly, it's quite insecure, but it is used in the POSIX and Windows operating systems. So here we have the diagram of a pipe where FD1 denotes the writing descriptor and FD0 denotes the reading descriptor. Now, a reading process will be blocked if it attempts to read more bytes than there are in the pipe. That means that the pipe has a fixed length, and if the reading process tries to read more than there are bytes in the pipe itself, then it gets blocked. And in the same way, if the pipe is full and the write process attempts to write in it, the write request is not accepted. Also, while writing into the pipe, the reading end has to be closed, and while reading from the pipe, the writing end has to be closed. So this ensures that there is synchronization and there is no concurrency or overlaps. Fourth, we've got signals. Now, signals are useful in inter-process communication in a limited way. It's nothing but a notification to a process indicating the occurrence of an event. So they're just system messages that are sent from one process to another. Now, usually signals aren't used to send data, but are more or less used for remote commands between processes. And software interrupt is, we don't know, it's not exactly predictable. So we can't tell when it can occur, and therefore it's called an asynchronous occurrence. Now, signals can either be ignored, which means they're blocked, or they can be handled using some sort of default action. So when a process detects a signal, it performs the default action, then handles it, and then closes the signal. An example of this would be pressing Ctrl C on the command line, which terminates whatever process you have started in the command line. These are some standard signal commands that you can see if you type kill space -L into the command line. Next, we've got shared memory. Now, the problem with pipes, first in, first out, and message queue is that two processes have to exchange information. Basically, the information has to go through the kernel. The server has to read from the input file, then it has to write the data in a message using either a pipe, first in, first out, or message queue. Then the client reads from the inter-process communication channel, and finally the data is copied from the client buffer into the client file, whatever the output file is. Now, this means that essentially two copies of the data are present, one at the input stage and one at the output stage. We can fix this problem using shared memory. Now, memory space here is shared between two or more processes. So the changes made by one process can be viewed by another process. Each process has its own address space, and if any process wants to communicate with it, then all it needs to do is form its own shared memory space from which other processes can view the information. The system calls used here are ftalk, which provides us with a unique ID, shmget, which provides us with an identifier for the shared memory segment, shmat, which is something that you use to attach the process to the specific address, shmdt, which is when you're done with the shared memory segment used to detach from the memory segment, and shmctl, which is to destroy the make sure that when you detach from the shared memory that it doesn't get destroyed in order to destroy that memory. This is used in POSIX and Windows, and here we have a representation of how shared memory works. So process 1 wants to share its details, So it creates a shared region from which process 2 can access and obtain the information from. Lastly, we have message queues. Now, message queues are simply a linked list of messages stored within the kernel and identified by a message queue identifier. So the sending process places a message onto a queue which can be read by another process. Each message is given an identification so that the processes can select the appropriate message. Now the processes have to share a common key in order to gain access to the queue in the first place. So messages are stored in the queue until the recipient process retrieves them, and as previously stated, the message is given an identification. Now, once the message is received by a process, it will no longer be available by any other process. So here we have a single message queue where only a single process is obtaining the messages compared to a message queue in which multiple processes obtain the message. These are the ways this is implemented. Now, why would we prefer a message queue over a shared memory space? Well, in shared memory space, the messages would be accessible by all the processes in the space. We may not want that. We may only want it to be accessed by a single process. There's also the chance that communication may be required only in small message formats. So there's no need to create a separate space when the messages to be sent are relatively small and easy to send across using a message format. Shared memory also requires a high frequency of reading and writing data. Therefore, it might just be more inefficient to use a shared memory space rather than a message queue. And finally, shared memory has to be synchronized. Yet again, the efficiency here comes into play. Only a few processes could also be present, indicating that shared memory is not necessarily required. So in conclusion, in this video, we've covered the following topics: processes and programs, types of processes, inter-process communication, synchronization and its requirement, critical section and race condition, advantages of inter-process communication, methods to achieve inter-process communication. Thank you, and I hope you learned something from this video lecture.